Okay, welcome back. Here's another balanced three-phased line or three-phase problem, power problem. So this is the English that they give you in the book, and I wish they would just give you pictures because what is it they say? A picture's worth 1,000 words, and this is just kind of crazy, really, to make you figure out what this is, and it's so ambiguous. And in life, you would never just go around, you would never write a specification with just words like this. It's kind of nuts because there's too much of a chance of it being misunderstood. You would supply a diagram, but they don't supply a diagram, okay? So I feel your pain. But anyway, here's the problem. A balanced three-phase line has an impedance of Z sub little l, 1 plus J8 ohms per phase. Remember, there's 3 lines, and this is the impedance of each one. Okay, this line supplies this line, okay, so one of these lines, so one of the 3 phases supplies 3 balanced 3-phase loads connected in parallel. So like, what does that mean? Well, what it means is that these 3 loads in parallel make 1 phase load. And I'll draw the picture. I might assign another problem that might talk about two balanced loads connected in parallel, and you should be able to adapt that. All right. Anyway, so they give you 3 loads, and they describe them in different ways just to get you thinking about how we talk about power. So load 1, this is load, L for load. Load 1 is 120 kVA. And so they're talking about S. When they give you volt amperes, they're talking about the complex power S, the magnitude of the complex power S. And with a 0.96 power factor leading, which means it's capacitive. And just write down these leading, lagging stuff and whether it means capacitive or not. Just write that down. So the angle is negative. Okay, S2, they're telling you kVA, so they're also giving you the complex power magnitude. And then they're telling you power factor lagging, so the angle is positive, right? Lagging power factor means a positive phase angle, theta sub phi. And load 3 is 100 kilowatts. So here they're giving you kilowatts, so they're telling you P, the average power by the units. And then they're giving you VAR over here, so they're telling you the Q. And then they're saying that it's magnetizing, which is another way to say that the angle is positive, that it's an inductive circuit. Okay, let's take this thing here and peel it apart. Oh, maybe I should ask what they're finding first. Maybe we should write that down, huh? Yeah. So find the magnitude of the phase voltage at the sending end of the line. The phase voltage at the sending end of the line, which is the generator. They're talking about V sub AN. When I draw the picture, you'll see. And then B, the percent efficiency of the sending line, which is a weird way to say it, with respect to the average power. Remember, average power is the big P. So in other words, they're asking for the efficiency of the sending line, right? They're trying to point out that the line has losses, and what are those losses? Basically, they're asking what percent of the total power at the source is lost in the lines. How much power is lost in the lines, basically? The percent efficiency of the sending line with respect to average power. How efficient is the transmission line? It's just the line itself, the wire. So how much of that is lost how much of the power at the generator is lost in the line? So let's draw the little picture here. So we can get by with the single phase equivalent here, which may not be obvious to you, but if you're not sure, draw all three phases and then see if you can do it with one phase. But it turns out we can do it with one phase on this guy. So they told us V sub AN, and here he is. So V sub little AN, they told us that somewhere. Oh, no, they didn't. Yeah, they didn't. But there it is. And then there's a line, there's a distribution line. Z sub L, that we have. That's this thing up here. Then this goes over to this goes over to the load. This is Z sub L, the load. And there's V sub big AN on this side. And then the confusing part is inside here, there's three loads that are connected in parallel. And the fact that they're in parallel doesn't even matter because we're talking about power. But there you go. So this is I sub A. Okay, that's the single A phase. There's three phases, B phase and C phase. If you're not sure, you could draw those out. It turns out this single phase is enough. So what are they asking you? So we're going to end up calculating the power at the generator. So we're going to need VAN and I sub A, and then we could get power there. And then if we had I sub A, we could get power lost through this. And then the ratio of the power generated to the power lost in here that's part B. Part A, the magnitude of the phase voltage at the sending end of the line V sub AN. Yeah, we need that. They're asking for that, V sub AN, but we're also going to need it for part B. All right. So before we go any further, it's good to sort of draw these guys, these things out. So first do the trig. Okay, so see, these are loads. So okay, there's load 1, load 2, load 3. And this dude here is a power factor leading, which means a negative angle. You look up in your little notes. And so basically it's a negative angle of something. And they've told you the 120 because they're giving you kVA, which is S. And they've told you that the power factor, which is cosine theta, is 0.96 lead. And so you work that out, and on your calculator, it's minus 16 degrees. The arc cosine would be would tell you 16 degrees. And then remember that big P is S cosine theta and big Q is S sine theta. So these numbers come out, and this turns out to be 33.6. This turns out to be 115, and this is minus 16. So just doing the trig on these two pieces that they give you. Okay, do the same thing on 180. On 180, so the power factor lagging means that it's a positive angle, and they've given you kilovolt amperes, which is 100, which is the S. And then P, decompose that the same way you do here. Just calculate the arc sine of 0.08, and you end up with 36 degrees and 144 and 108. And I'm sort of skipping the trig, but that's not that hard, right? Do the trig. Okay, then this dude here, they're telling you it's magnetizing VARs, so that's a positive phase angle, and they've given you the P component, and they've given you the VAR, which is the Q component. And with Pythagoras, you could figure S. S is root p squared plus q squared. And you could use arc, tangent, and such, and you could get 8.8 degrees in here, and this works out to be 102. So I skipped some of the detailed steps, but go review your triangles, and this is enough information to construct these dudes, as long as you keep in mind what leading, lagging, and magnetizing means, and then the units, the different units of powers, volt amperes, kilowatts, and bar for P, Q, and S. Okay, so that's what's going on. Okay, our strategy is we're going to use this S per phase is V phase, I phase conjugate. Use that, and then we can use, is it Ohm's law? Probably, right? Let's see. We're going to use Ohm's law, probably. And then there's going to be a KVL in there. Yeah, okay. That's the strategy. So, the thing to realize is that they're giving you these load powers, sort of like there's like, what are they talking about, right? It's like there's load 3 and load 2 and load 1, but all three of these is like S phase. We're talking about power, so you can just add them. I mean, don't let the parallel freak you out. Yeah, they're connected in parallel, and if we were asking for impedance, right? If we were asking for impedance of total impedance, then you would have to use the parallel impedance simplification formula, right? The product over the sum, or I guess there's 3. So you'd use the reciprocal of the reciprocal of the sum of the reciprocals to do impedance. But we're not talking about impedance. We're talking about power. Okay, so you can just add them. So I should even write that down. So the S phase is just these three. It's just these 3 loads together. That's the trick. It's power. It's not impedance. Not sure how else to say that. So I'll write these in rectangular, just using the P and Q. So this is 115 minus J33.6. That's level. That's L load 1 or power 1, really. And this thing is 144 plus J108, and then this dude is 100.8 plus 15.6, and that works out to 359.8 plus J90. And sorry, I'm reading ahead and getting okay. Anyway, so now we can use this S phase is V phase I conjugate. We can use that to get IA. So specifically IA conjugate is going to be S phase over V phase, and so this is 359.8 plus J90 over where's that? Oops, that was given. I sort of forgot it in here. So another given is the line voltage at the terminals of the load. line voltage at terminals of load V sub L is 2400 root 3. It's another given I left off. So they're telling you the line voltage, which means line to line, at the terminals of the load. So they mean A to B. So there's another big parallel box of goodies in there, and then another big parallel box of goodies out to C, up to terminal C, and this is out to terminal B. They've given you this thing here. This is VL is 2400 root 3, but we need the VA. We need the phase part of that. So the root 3 is your clue here, that the phase voltages are root 3 smaller. So this is just going to be 2400, and then just make it a reference. So because they're not giving us any angles in here for these voltages, so they just gave us a magnitude of VAB, but we need VAN. So take root 3 and then just assign 0 degrees as our reference. All right, so that's answers now. So this is 149.9 plus J 37.5 amps. That's IA AA conjugate. So IA is so that you could do this in polar form, by the way. IA conjugate is 154 with an angle of 14 degrees amps. So IA would be a negative J or a negative angle, so 154 angle minus 14 degrees. So that's IA. What are we trying to do here? Yeah, so we have this voltage here. Now we could, and we have the impedance. No, but we have this voltage here, and we have this current, and we have this impedance. So we should get VAN now. So by KVL on the single phase equivalent. So loop A, really, the single phase equivalent. I'm just talking about just this loop that I drew here, because the previous problem we had another loop, which was a lot of fun, but here we just need the single phase loop. So VAN, if you do source equals load, VAN, this VAN voltage plus up here is dropped across this load, which would be ZLIA, and then it's dropped across this VAN. So it's going to be the voltage dropped across the line, you could say, plus the voltage dropped across the load, you could say. And by Ohm's law, V sub line is IA Z sub L. It's the current through this distribution line times the impedance plus straight out VAB, or I'm sorry, VAN. So this is I sub A is 154 angle minus 14 times Z load, or Z line. Z line is 1 plus J8. It's the impedance of the line in this little box here, plus the voltage dropped across the load, which is 2400 angle 0. Okay, so that works out to be 3087 angle 21.9 degrees volts. That's V little a n. So V, so V phi, no VL. VL, no. What are they asking for? The magnitude of the phase voltage at the sending end of the line, VAN. Yeah, that's the answer. Well, they want the magnitude. Well, here's the magnitude. Okay, that was part A. What did we do? You got to realize that you can add power, and when they say this 3 loads connected in parallel, because they're saying there's a line. This is the line, and that line is supplying 3 balanced 3-phase loads connected in parallel. So it's balanced 3-phase, and there's also this thing in parallel. I mean, the only way you can draw it is like this, with another 3 boxes in parallel. So you got to realize that, and then you got to realize that because they're talking about power here, 3 powers coming out of this, that you can just add power. And and then there's this relationship between the line to line voltage, AB, and then AN. Choose one of these as a reference angle. And power formula to get the current, KVL. All right, that was part, whatever part that was. Then part B, percent efficiency of the sending line with respect to the average power. What percent of the total power at the source is lost in the line? So we need the total power here, and then the power lost in the lines. Which we sort of have, because we have the power at the load. If we had it at the source, then any difference between the 2 powers here must be lost here. That's the thing to realize. So this is part B. I guess this was part A over here. But part B, we need to find the power at the source terminals. Little ab. So the power at little ab is just V at A. I'm sorry, AN. The voltage times the current. It's VAN I A phase conjugate. That's our power formula for at the source. So this is where do we have this? Do we have this value here? Yeah, we just solved for that. So this is 3087 angle 21.9, and we need the conjugate of this thing, I sub A conjugate. So it's 154 angle 14, and it's 385.2 plus J 278.7, and we're talking about S, so the units are volt amperes. And then if you wanted it in polar form, which we don't really need, but here it is anyways, 35.9 475 angle 35.9 kVA. So the percent efficiency. So so this guy. See, this is the power at the source, which is, I guess, power at AN. I guess you could say this is 385.2, and the power at the real average power at the load is in here somewhere. We did that already. It's here. The total power lost at these three dudes here is 359.8. This is 359.8. So the difference between these it must be in the power line, right? Because we calculated the power here, the voltage across here, and the current through it gives you the power. And then we had previously calculated the complex power here. So the difference between these two is this. So it's going to be, what is it going to be? You could do it, you could do 359.8 over 385.2 times 100. It's going to give you 93.4%. That's what's used in the load. So 100 minus 93.4 is 6.6% used in the lines in the distribution line. That's the answer. 6%.